Hello everyone. In the previous lecture, we were discussing about virtual displacements. And usually, when we come across these virtual displacements in certain textbooks, uh, oftentimes we see that the next topic is the principle of virtual work, because of course it is intrinsically connected to the concept of virtual displacements. However, there is a missing link in terms of the requirement or the motivation of considering the principle of virtual work. So what we'll do is we'll discuss the principle of virtual work, certainly, but before that we will discuss something which is all very familiar to us, and through that discussion we'll see what is the motivation for discussing the principle of virtual work. All right. So the first thing we are going to discuss is the law of kinetic energy, which you all know, but nevertheless, I will discuss it. So in the lecture notes that I'll share with you, the formal statement of this thing is given. So I will not rewrite it again, but I'll just discuss it here. And the law of kinetic energy, it tells us that the work done by all the forces, and mind you, when I say all the forces, I include all the external as well as the internal forces that act on a mechanical system. So the work of all these external and internal forces that act on a mechanical system, it equals the increase of kinetic energy of the system, of that mechanical system. This is what the law of kinetic energy is telling us. So how can we put that in terms of some equations? So uh, so you please note that this is very important. Before writing an equation, that the work done that is involved is due to both external and internal forces, and that is equal to the increase in the kinetic energy. Okay, so I've written in a very informal fashion here. So the work done for a mechanical system uh, between the times t0 and t1, so we'll consider it to be like this. So usually we are familiar with this kind of an expression, f dot dr, where dr is the infinitesimal displacement, but uh, there are certain disadvantages to writing like this. Okay, I mean, it can be quite a detailed discussion. uh, I won't go into that much detail. So you think about this. uh, okay, so think about this part. I will not write like dr vector, and if you have some doubts we can discuss it during our doubt clearing sessions. So instead of this, what I will do is I will write it like v dt. Okay, so with the understanding that v is like this. Okay, but it makes quite a bit of difference when we write in this alternative fashion. Now this f vector, we can write it like mass times the rate of change of the velocity, which you all know from our basic principles of mechanics. And this entire thing can be written as half m ddt of v dot v. So you understand what is going on here. So this is so if you do a chain rule decomposition of this derivative, you will end up with twice of this term. So which is why we have the half here. So overall, what we obtain is something like this. Okay, and you understand that this entire entity overall is nothing but the change in the kinetic energy. All right. So, uh, so this is just the statement of the law of kinetic energy written in terms of the variables involved. But this is not the end of it. We have to understand a few very important points associated with it. So the first thing that we have to note is that uh, the law of kinetic energy. Uh, so the law of kinetic energy, it is restricted to inertial frames of reference. This is very important to note. To inertial frames of reference. Now, you can understand that in different inertial frames of reference, the accounting of the kinetic energy will be different because the velocities may be different, which means that uh, with changes of the inertial frames of reference, with the choice of the inertial frames of reference, the work done associated with the kinetic energy, that also changes with value. Okay, so this is not an implication of the law of kinetic energy, but this is something that you have to remember when talking about the law of kinetic energy. Okay. Uh, Next, what is the implication of this law of kinetic energy? So, as I said, the whole point of discussing this law of kinetic energy is to motivate ultimately the discussion of the principle of virtual work. So, how do we make that step? How do we proceed towards that? So, as a first step, we need to appreciate that as a direct implication of this law of kinetic energy, we can think that when a mechanical system is beginning to move, okay, then certainly it is gaining kinetic energy. So, uh, mechanical system begins to move, which implies that the kinetic energy is increasing. Now, directly from the law of kinetic energy, what we can say is that the work done by all the external and internal forces on this mechanical system, when this delta K is increasing, that work done must also be positive. Okay, so okay, work done due to external and internal forces must also be positive. So, can we not conclude from this that uh, for a mechanical system, uh, so when we are considering this mechanical system, it is not going to move spontaneously unless uh, it experiences some kind of arbitrarily small displacement in such a fashion that the work done by all the external and internal forces is positive. So I repeat, the implication of what we have just said here, that when a mechanical system begins to move, the kinetic energy is increasing, and as a result of that, we have to conclude that the work done on it must also be positive by the law of kinetic energy. So, in other words, what we can say is that a mechanical system will not spontaneously start to move unless the unless it is unless for some arbitrarily small displacement, the arbitrary small displacement has to be in such a fashion that the work done uh, by all the external and internal forces is positive. Okay, so it's just a different way of looking at things, but it has a tremendous implication. Okay, and that implication is captured in what is referred to as the Fourier's inequality. Now, this Fourier's inequality is something which we don't often come across in our undergraduate textbooks of mechanics, but historically it has an important place. Now, and it is something which is the precursor to the principle of virtual work. Now, before we discuss quickly the Fourier's inequality, let me just tell you that when I mentioned that a mechanical system, it does not spontaneously move unless for arbitrarily small displacements, you have to understand that all those displacements that we think about for this mechanical system, if you take your conceptual understanding back to what we were discussing in our previous lectures of energy methods, we can think of them as changes in configuration. And mind you, those changes in configuration can be brought about by virtual infinitesimal displacements. Okay, so as long as we proceed by admissible paths respecting the constraints of the system, we are free to explore various different configurations. Okay, so you take a configuration, you take a sort of neighborhood configuration going by an admissible path. So when I say a thing like that, I basically mean that you are imposing a virtual displacement, a virtual infinitesimal displacement on it, and then thinking about the kind of work done that is involved, whether it is positive or what. Okay, so so the implication of this law of kinetic energy, it can be summed up in the something called the Fourier's inequality. So that is the next topic here. And what the Fourier's inequality, it tells us, okay, again, I'm not going to write the statement here, the formal statement, because that is already written in our lecture notes. So what it tells us is that a motionless mechanical system, it remains at rest. Okay, a motionless mechanical system, it remains at rest if the virtual work done by all the external and internal forces, that is very important, just like in the law of kinetic energy, it is less than or equal to 0 for every small virtual displacement that is consistent with the constraints. Okay, so just to capture the important points of this, a motionless mechanical system remains at rest if the virtual work so you can somebody can point out that we have not really gone into the principle of virtual work, so why are we stating something like virtual work? So you understand that this is just the work done associated with a virtual displacement, which we have already talked about in detail in the previous video. So a motionless mechanical system, it remains at rest if the virtual work done by all uh, external and internal forces is less than equal to 0. Okay, so that's it. Now in more concrete terms, beyond these abstract statements, you consider the simple example of a brick resting on a table. Okay, so you think of it like this, that we have a brick resting on a table. Now suppose we imagine that this brick, it slides a little bit, either to the left or to the either to the left or to the right. So friction will perform negative work. Okay, so why do we say negative? So because you understand that the direction of the friction force will be opposite to the motion of this brake. Okay, so the work done on this brake is going to be negative. Now uh, so that is directly connected with what we have here. Okay, so because it is less than equal to 0, that work done by the friction. So what we were thinking about as a possibility of motion is certainly not a possibility. So as far as friction goes, this motionless brake will continue to remain at rest. Okay, so there is no danger that friction will automatically initiate some kind of motion uh, of this brake, which of course you all know intuitively. Okay, so of course a brake which is resting like this is certainly not going to be initiated into motion because of the friction. Rather, the friction retards the any possibility of motion. Okay, next example is that suppose you imagine that this brake, it spontaneously tilts like that. Okay, so instead of like that, it may be just one end of it just lifts up. In that case also, the force of gravity will perform a negative work on this, and so that kind of a virtual displacement we are thinking of, uh, that uh, uh, that will imply a negative virtual work, and so from the point of view of gravity also, this motionless mechanical system, it remains at rest. Again, you think of so I'll not go into the detailed discussion of this, but I'm just telling you that suppose you imagine that this breaks, just hops like that and comes back, then what happens? Okay, so my question is whether the work done is negative or zero. So you think about it and you'll get your answer. Okay, so the answer, of course, the ultimate answer is that that kind of a hop is also an impossibility, which you know physically. Of course, if you think about it physically, spontaneously, it's certainly not going to hop like that. Uh, but in terms of the Fourier's inequality also, that kind of a motion is certainly prevented. Okay, but now there is a subtlety, a very important subtlety involved with this Fourier's inequality. And that subtlety is that whatever inequality we are talking about here, that the virtual work done by all the external and internal forces is less than zero, that uh, is only a sufficient condition. Meaning that if we find, okay, so Fourier's inequality is only a sufficient condition. So if you find out that the work done by all the external and internal forces for a virtual small displacement is less than equal to zero, then it is guaranteed that the motionless mechanical system will remain at rest. There is no problem with it. However, if you find that this inequality is violated, then you cannot conclude necessarily that the body cannot be at equilibrium. Okay, so let me repeat that. If you find that the work done by all the forces and internal is less than equal to zero, then you are guaranteed. It's sufficient for us to for that. It's sufficient for us to conclude that the motionless mechanical system will remain at rest. However, if we find that this inequality is violated, for example, if we find that for a certain kind of motion, the virtual work done by all the external and internal forces is greater than zero, then we cannot conclude for sure that the motionless mechanical system cannot indeed be in equilibrium. Okay, so the example which is usually given for to illustrate this thing is we take a dome like this and you place a little marble here. Okay, now you know that this marble or this little ball is in a state of equilibrium at the top position of this dome. Okay, it's not a stable equilibrium, but it is an equilibrium condition. Okay, so what happens is that if you slightly perturb it, it will just drop off from here. So in terms of the virtual displacement, if you displace it by very little amount here, then it may appear like the work done by the force of gravity, it will turn out to be positive. So this Fourier's inequality is violated, and that may tempt us to conclude that this thing is certainly not in equilibrium. But that would be a wrong conclusion because this position is very much in equilibrium. It's not a stable equilibrium, but that's a different story. But it is in equilibrium. Now, this kind of an like a violation of the inequality takes place because of some issues uh, with the orders at which we are calculating the work done. So there are certain subtleties involved, which I'm not going into right now. Uh, but the fact remains that the Fourier's inequality only gives us a sufficient condition. It does not give us a necessary condition. So it would be very much useful for us to obtain a condition for equilibrium which is both necessary as well as sufficient. Okay, so this is not necessary. This inequality is not necessary. So we would like to find out, okay, so this is the main uh, outcome of all this discussion, that we would like to find some condition that is both necessary and sufficient. And it is this condition, it is our quest for such a condition which leads us to the principle of virtual work, because that principle of virtual work will be giving us both a necessary and a sufficient condition. All right, so in the next video, I'll conclude the video here. So in the next video we are going to discuss the principle of virtual work, but before we discuss that principle of virtual work, we'll have to discuss uh, a uh, a little uh, a little extra thing which is called the work function. Okay, so there's a subtlety involved there also, so we'll discuss that, okay, in the subsequent lectures. All right, thank you very much.